here. So I'll just go through the homework backwards. I think this is 7 and 8's out there too. So I'll maybe do 8. Maybe a minute. So he has this thing where he's talking about all of this, the Bernoulli's equation. And he gives this example, which I don't know if I touch that. It doesn't give me bigger. I guess I can make it bigger. And so let's sort of set this thing up, and then we'll look at the thing. I'll basically do, we'll do rectangular. We'll do a new, I don't know. I'll do that. Okay. What are you doing? Let's see. I had to restart the computer because everything was geeking up as far as the pen and everything. We'll go in here. Okay, so if you're going to run Bernoulli's equation on this, looks like he has 4 different identified locations. And so I'm going to basically follow that, his identifications, without really making a comment about them. And so I've got A, and I've got B. It looks like to me, put a little dot right there. Looks like he has D right here and then C right here. So what I'm going to do is Bernoulli's equation has a pressure, an unknown, a Z, and a velocity. So if I list A, B, and C, and D, I'm not really shooting to put the actual values in there in so much as just do I know them. So I've got that. So I know it squirts out here at C. I don't know the velocity, so I'll put a little question mark. I do know the elevation, and I do know the pressure. So the elevation is pretty easy. It's 0. And then the pressure is 0 because it's shooting out. So this should be a big asterisk in that the number of unknowns I've got is 1. So if it B, if I, let's look at A first. If I look at A, I would definitely know this. And if there was a hole in this so that this was atmospheric, I would know that. And so let me write those down. So I'm going to assume it's atmospheric. And so in other words, there's a little vent somehow, even if it's up under here, somehow up in the top of this thing, it's atmospheric pressure. I know it's 60 foot high. And I know that there's a lot of surface area here compared to the surface area of the pipe. So I'm going to say it's okay that it's close to 0. Now you have to remember in Bernoulli's equation, it's squared. So if you take that squared, you know, if you get 0.001, so the water's creeping down really slow, then that becomes a much smaller number. It's pretty insignificant compared to that. So it's okay to make this assumption here in a case like that. So here, this is really great. This is like, I know I have no unknown. So that's my target spot. That's where I can find the actual constant. Oh, anyway, the constant. I can actually find the constant right there. I can, if I wrote between here and here, I could solve for that value, which is the velocity. Now let's look at D. At D, I know the elevation. I don't know the velocity. I don't know the pressure. Okay, let's look at B. I know the elevation, which is 60 minus 8. What is that, 52? I don't know the pressure and I don't know the velocity. But here's the key. If I go in here, go away. If I go in here and write between here and here, Out of that, I would get the velocity at C. And if I had the velocity of C and I knew the diameters of all these sections of pipe, from that, I can use continuity to get the velocity of D and the velocity of B. If I did that, I would have all of these. If I had all of these, there would only be one unknown in each one of these, and that would be the unknown. So I can jump from A to C to find what I need, the flow rate coming through here. And once I have it, I can back up and find the pressures anywhere in there. Now, I don't even know what he actually asked us. Oh, they got it fixed. Okay. So now let's go back and see what they asked us. Okay, that's not, is that it? Okay. The elevated store. Okay, so he tells us all this, and this is all great. We're going to use this equation. That's good. Oh, that's kind of cool. But semi-useless. He says the elevated tank is filled water to the depth shown. A is the standard. A is at standard pressure, so it's what he's saying. There's this vented tube here. What's that say? Caption. The figure of the elevator. Oh, okay. When the gate valve at D is fully open to determine the velocity at C. Okay, so that's your first step towards this. And so he's just basically saying, I want you to focus on the connection between the A and the C and to solve that. So he's leading you into this. So you just, PA, which is what you're interested in, gamma, ZA. Now he writes his as rho G, Z. If you look back, he's doing this. He's taking the pressure, the density, and putting it under there. So there are three forms of this equation that all work. What is this? Oh, that's a freeze warning, I think. Okay. So, so he's writing. Okay, I'll write all three forms of the equation. Rho velocity A squared over 2. The other is equal to a constant. Now I'll finish this up. The other one is pulling the density under here. If you do this, rho times that becomes just G times Z plus V squared over 2. I'll talk about this in a minute. So then the other is you take this, V squared over 2, and if you brought that under there, you'd get a G under here. So essentially, this is equation 1. So you take equation 1, you divide it by the density, you get this one. You take equation 1, you divide it by gamma, you get that one. I'm about to make a statement which is truly not always the case, but civil engineers like this one. Aerospace engineers like this one, and mechanical engineers like that. The reason being, it's very weird. One is the civils is very straightforward. They will see everything from an elevation. So they're standing up on top of a mountain. They're looking at a lake, and there's a pipe in there, and they're going to send the water down the hill, and it's going to go flood this other basin. And they're going to set up that little tripod, and some dude's going to stand over here, and he's going to put that little thing in there, and there's another dude over here, and he looks through this big scope in it, and he says, whoa, he sees the elevation. So everywhere they're shooting, they're using the transient to shoot the elevation. This puts the equation in their realm of reality. So the energy could be thought of as an elevation of stagnant water. if you want to look at it. So this lake is sitting stagnant. As it flows downhill, it's going to be, what's going to happen is, if it flows in an open channel, okay, let me see if I can make it do that. Okay, so let's say they have a piece of pipe. Okay, let me see it. I've seen them do this before. They take a piece of pipe, and then the water kind of goes, if it gets too high, it goes over that piece of pipe. And then what you really want is you want the water to squirt out on the ground, and it goes down an open channel as it goes down this hill. So as it goes down this hill, pressure is the same here as it is here. So the civil engineer will say, well, as it's going down fast, more of the hill, it'll go faster and faster. The same thing occurs if you go and open your faucet. Okay, so you open your faucet. This is a bad picture of a faucet. Okay, so here's your faucet. You open it. There's a pipe back here. It starts coming out of your pipe. What does it do? It starts narrowing down until eventually it comes out so slow that the surface tension breaks these into little bubbles. Why is it necking down? Because if I look down here, it's going faster. This is faster. This is slower. You look at this area, the area, in order for these to be, let's say, the area slow, area fast. So the area fast times the velocity fast is equal to the area slow, velocity slow. So if this area were, say, just 1, let's say this is 1, and then as it went down further and further, this became 5, then this has to be 1/5. The area has to neck down. So a civil engineer will see that as you go downhill, it's got to pick up energy from somewhere. So a civil engineer sees that. They like it written that way. It's historical in the sense that they often will look and see, contour maps, and you can see them on Google Maps. So you're like, okay, water always flows downhill, right? And then you got this little ravine here. It's going to flow into this ravine and head off down that direction. So you look at your gradient of the hill, and that's going to tell you some information. But this is a straightforward measurement of feet. Mechanicals, they really like PSI. Okay, so they want to see, pressure in the pipe and stuff like that. In aerospace, let me kind of do it like this. Aerospace, I've seen aerospace see things more that way than this way, actually. But there are a few aerospace engineers that like to see it that way. I'm not exactly sure why, except, if you think about it, we're used to seeing PV is equal to RT, right? Or pressure is equal to rho RT. But pressure over rho is equal to RT. So suddenly they see this term as looking a lot like that. And there's some evidence that there's some people that are in aerospace that like to see things like that. It doesn't matter. It's the same equation all across the thing. So I'm going to stick to the mechanical approach. And we're just going to write it here. But at least what I'm trying to get across is the equation themselves are the same. It's just they're scaled different. So here, let's write between A and then C here. So all you do is repeat this. Okay, now the thing is I can just start grabbing the stuff out of A and sticking in there, and I can say 0 plus 60 times gamma plus 0 is equal to, and I'm not going to write that quite yet. So gamma for water is 62.4 pounds per cubic foot. In his case, he tells us 1.94 slugs. That's a standard. Okay, so if you look at rho times G, that'd be 1.94. slugs per foot cubed times 32.2 feet per second squared. And if you multiply those two together, you're going to get 62.4. But that's going to be slugs foot squared over second squared. And you're looking at that and you don't like it until you realize F is equal to MA, or a pound is equal to a slug a foot second squared. And then if you want to replace that, a slug is equal to a pound second squared over a foot. So now you take that and you put over that, and you know, the one way you can do this is take this and say slug foot to the -2 second to the -2, and this is going to be a pound second squared foot to the -1, and you take all that and you put that right beside that, then you're going to replace the slug with this, and you're going to get a pound a second squared a foot to the -1 from here, and you're going to get a foot to the -2 and a second to the -2. This will cancel that, and these two will add up to be a pound over a foot cubed. So through all that mess, what you kind of determine is that the units are the same. And so you're sitting here looking at that. So your energy is 60 and 62.4, or something in the neighborhood of some number bigger than 1. Oh, that's crazy. 3,744. Now, for a mechanical, they didn't see that in pounds per square inch. They see it in pounds per square foot. Why? Okay, let's see if we can get this part out. Okay, this was in feet. 60 feet times 62.4 pounds per cubic foot. So that'll give you a square. That's what that comes from. And then you got your pound on the top. So if you want to turn it to PSI, I would suggest waiting a few minutes. Now we look at C, and we know the pressure and the elevation are both 0. So now I get rho. Let me look back at something real quick. And his. Okay. That's a little strange. I don't like that other notation, but that's okay. Sorry. So here I get the 1.94, because that's what the density is. And then I don't know what the velocity of C squared is. And then I don't know anything else to do but just to put these down together, 1.94 over 2, then VC. Let's play with the units over here. So the units of density is slug per cubic foot. The units of velocity n squared is going to be feet squared second squared, and 2 doesn't really have a unit. So you're multiplying these two together, you get slugs. Okay, and then I get, so I have 2 of these on the bottom, 1 of those on the top, and then I have foot, and then I'm going to have a second squared under there. Or I'm going to have it like this, a slug foot to the -1 and second to the -2. Do the same little experiment. F is equal to MA, or a pound is equal to a slug foot per second squared. So a slug is going to be equal to a pound second squared, a foot to the -1. So I'll take this and I'll stick it in for this. So I get a pound. Second squared, a foot to the -1. Then I copy this down, a foot to the -1, and a second to the -2. This and this are gone. And these two come together to give me a pound per foot squared. So even though initially it doesn't look like it, this is actually pounds per square foot. Sounds weird, but that's kind of what it is. And we'll just move that out of the way. I guess technically that should go with that. So now I can get VC is equal to 3744 times 2 divided by 1.94, but I got to take the square root of it. And so if you do all that, you're going to end up with, and that is if I think I did copy it down correctly. 62.13 roughly. Now, that'll be in feet per second squared. I don't know. I have no idea. Oh, it put it down in feet per second squared. I'm just going to put in the 65 just to see what it does. Well, okay. Didn't like that. So go back to 62, I guess. I would think that would be close enough. Oh, really? What if I just put 2 without the other? Okay. Oh, 62.2. Okay. Yeah, that's close enough. I don't know what oh, there's a C too. Okay, the elevated storage tank. We calculate the pressure at B when the gate D is fully open. Okay, the water flow stuff at a constant, velocity of 10. Calculate the pressure reading on gauge C when the pressure at A is 45. Let's play with C for a minute, because this one's just a matter of, this one's a matter of taking now. Okay, so he says where is it? D is fully open. Well, it's fully opened up there. So in other words, now that if you take this little chart and you say, okay, now that I've gone in here and I've figured out this, okay, wait a minute, I've figured out this, we can use continuity to find this one and this one, given the fact that actually I don't think the pipe diameter changes, so I think in actuality these are all the same. Then he says, I don't know what he says. Did he say find it in B or what did he say? Pressure at B. So then you're basically using this 52 and this to find that, because this is, so after you find this, before you solve it, here's what you got. Okay, I'll tell you what, let me get some of this off here. So the solution method, this is kind of, let me see if I can go in here and take out these extra things here. So if I go in here and look at unknowns, and so this is kind of a weird way of doing it. So I have no unknown, currently I have no unknowns here. I have 2 here, I have 1 here, and I have 2 here. The only thing I can do is write between here and here. Once you have that, you've got 0. You've got 0 unknown. But what do you do here? You still have 2 and 2. So to get from here to here, I did Bernoulli's between A and C. So I did Bernoulli's between A and C. Now I'm going to do, I'm going to do continuity between B, C, and D. B, C, and D. So this is this. Now what I'm going to do here is do the continuity. That will reduce this to 0 unknown, 1 unknown, 0 unknown, 1 unknown. Why? Because the continuity told you Bernoulli's fixed that one. Continuity in the next step fixed these two. Now I do Bernoulli's again between, and I would do it, okay, I would do it Bernoulli's between A and, because this is the one that I was given all the information. This is a special one here in that I know that what's happening here. So I would do it between A and B, and then you would have 0 unknown, 0, 0, and 1. And apparently he doesn't care about that one. Now what he's done, he's changed the problem. What has he done? On C, he said the water flows through the pipe at a constant velocity of 10. Calculate the pressure reading on gauge C. Calculate the pressure reading on gauge C when the pressure at A is 45. So you have to redo your table. Okay, wait a minute. Here's how you redo your table. Let's see. Probably the best thing we're going to do is copy the table, and I'm just going to copy my table. We'll copy, move over to the side, sort of drop the thing. Okay, so what has he done? He's monkeyed with this whole problem statement. So what he has done, let's see if I can figure this out. So he has told us in no uncertain terms, for some weird reason, the water flows through the pipe at a constant of 10. So he's told us this. He just told us this. So now we got a problem that he's not discussing here, in my mind. Okay, and let's take a look at this. He says, calculate the pressure reading on C when the pressure at A is 45. Okay, so the pressure at A, 45. So he's pressurized that top. Okay, so what really bothers me, I got 62, but he's pressurized the top, and he's got 10. So there's got to be something else going on. What he's got going on is taking that pipe D and closing it partially shut. Okay, so that's okay. But what he's done, he said it's 10, and we're going from C to A. So we ignore the rest, and we're going from C to A. So now I still sit there with that, but he's telling me, wait a minute, let me go back. Calculate the pressure reading at gauge C when the pressure at A is 45. So there's a little bit of a contradiction here because it's dumping out in the atmosphere. The only way that can happen differently at C is as if something is backing this up. It's going to be 0, but this is a little bothersome. So he's going to ask you for that. But logic, you look at it, it's got to be 0. So anything I'm thinking is, he probably didn't say this, is he's attached another piece of pipe to it. And C is now at that particular point and can't be atmospheric for that reason. So all you're doing is here you have 0 unknowns, here you have 1, and you just solve it and you just go with it. So it doesn't make physical sense to me in the sense that there's more description that's needed. Does that make sense what I'm saying? You can calculate the pressure reading at on gauge C Man, I'm guessing that's the C, the location right there. On gauge C, when the pressure at A is 40. I mean, technically you could have that. If you did something like that, if you did this, say you had the pipe that was shooting water out, and then what you did is you just slipped around a little cover over it so that it kind of did this. That would bump the pressure up away from atmospheric, which is out here. And so suddenly it's shooting out here. So you had C here. Well, now you have a new location E that you, but he didn't say anything about affecting it that way. He just said that. So that's the problem a lot of times with stuff like this. This is the second edition of the book. He's done a very good job for this being only the second edition. But there's a few things like that when you look at it. You need a couple extra cents to make an engineer feel more comfortable with it, if that makes sense. Oh, it could have been. Yeah, it could have been. Because what's funny is, yeah, it could be. But then method you calculate can be the same way. So because C and D, I mean, they're at the same elevation. So, but it's okay. If you just calculate it and put it in, it should work. It's just annoying a little bit. So, now let's see, what's the other one? Okay, so how do I do this? Oh, I go to the right. I don't really care. Can I just make it go anyway? Okay. So I was making a comment about civils, and I should be nice about it, but let's take this picture and I'll show you. This is a good one for the people who like civil. So here he's done this. Okay, so he's done that. Ooh, wait a minute. Okay, so we'll take the picture, and I'm going to add to the picture so that we kind of get a feel for. Ooh, that's weird. Okay, wait a minute. I want to do this one. Okay. So let's take this picture, add to it, and add a little extra logic to it. And here's what I mean. So first I'm going to take it down the page some. And does he really, just to be precise, okay, the hydraulic, I just want to read it to make sure I can figure out whether it's flowing left or right. Okay, to understand the hydraulic, that's all great. Water flows in the pipe shown here. The velocity A is that. The pipe diameter is that. It does not change until the expansion. Oh, okay. So that implies to me it's going to the right. Okay. So let's do it like so. Okay. So if it implies it goes to the right, I'm going to make this problem kind of fit the way civil engineers like. So here comes the pipe. And it comes way back here, and it's sitting in a reservoir. Let's say it doesn't change, and then it's in a giant reservoir. So then what they'll say is okay, this is what they call the energy line. Assuming the flow is going that way, it doesn't matter which way it's going, but we're going to assume it goes that way. So then we're going to do this. The pipe goes on up to another reservoir, and there's no losses. Now here, let's not make it turn quite yet. We'll make it kind of go up here. And then suddenly it comes to another lake. Now, this sounds weird, but the energy level here is the same. So if you had two lakes sitting that way, there would be no reason for water to flow. So what you've got to do is you've got to figure out how to make this thing, water goes downhill to make it keep flowing downhill. So what happens though is they've got these. Okay, he used the big capital letter H. P over gamma plus Z, and I'm just, and then V squared over 2G. So you look at this thing, and I'll henpick all the things. So first, this is in feet. And now this one is in pounds per square foot, and gamma is in pounds per cubic foot. So if you look at the units here, it's in feet. So you look at the units here, it's feet squared per second squared, or I'll do it this way, feet squared second minus 2, and then a G, that's in feet, okay, and that's underneath second squared B on the top. So here you get feet as well. So everything is in units of feet. Now what happens to this is if you stare at this long enough, you find out something interesting. Okay. So you sit here and look at the energy level of that. That's fine. But as the particle of water goes down here, it starts speeding up. So when you're down along in here, what you're finding out is the energy level kind of goes like so. So now you get a portion that is the V squared over 2G, because up here it wasn't moving. There wasn't any speed to it. So suddenly you got that. So what happens is that's the rest. You P over gamma. Well, plus the Z. And so you'll get these changes like that. And so that's the way civil engineers look at this, as the water is flowing. But in reality, what happens is this: the energy is losing ground. So you're going to have losses, and these will be considered losses. And we can deal with that later. It used to be chapter 8. I don't know what the chapter is now. So let's go back to what he's saying. Okay, he says all this. The pressure at point A is that. What's the hydraulic head at point A? Oh, okay. So what he says, divided by this, H represents the total head, each term, and then you've got the energy grade line, and that was the energy. And then you go down here, and it says the hydraulic head includes just the pressure and the gravitational potential, which is this two term. The plot of this quality system reveals the hydraulic grade line, the HGL. So I kind of was producing that along here. So that's the hydraulic grade line. This is basically the kinetic energy. So it's the total head minus the kinetic energy. And the energy grade line is always the kinetic energy. So EGL. So then what's he wanting to know? The hydraulic head at point A. So, okay, the hydraulic head kind of to me means the hydraulic grade line. So it'd be these two by themselves. It's not, it would be these two by themselves. And this is what he called, let me make sure I get his notation. He called energy grade line is always the kinetic term. So he says this is the energy grade line, and this is the hydraulic grade line. So I always look at it as this is the kinetic energy, which so he wants to know this, the hydraulic grade. The reason there's a line there is because most people drew them as lines out here. So what happens here, okay, and I should be a little bit better. So it speeds up. Well, right in here, it starts slowing down. And the reason it slows down, it reaches this little place. So the velocity here is faster than it is here because of continuity. And so this thing shrinks back. So you get this thing, then it shrinks back because it expands there. So he wants to know P over gamma plus Z. His datum, he already gave you his datum, so you got that. This is kind of really, it's 310 kilopascals divided by the gamma. And that should be the value that you put there. This is what the view hints say. Hint 1, how to approach the problem. The hydraulic head is the sum of the pressure and the gravitational force. Identify the values required to calculate this quantity. Well, you put the datum here. If he's asking about A, the datum is 0. That's 0. So P over gamma. Calculate the specific weight. Okay, did he give us that? It's usually, if it's water, it's usually 1,000, but he's written down a different number. So the hydraulic is a specific weight. However, only the density, which usually I put in 1,000, is given. Calculate the specific weight of water. Well, you take 1,000, you multiply it times the G, which gives you 9,810 or 9,801 or 10. And then, okay, so then you take that, you take the pressure, divide by that number, and you got your answer there. Hint 3, what? Identify the height at A. The height. That's got to be, what do you mean to identify the height at A? The elevation term, and here's a Z, the height of point A is the highest point of interest above the datum line. What is the height at point A? That's kind of like,
I guess it's talking about the center.
I'm going to try something just crazy. So, okay. All right. The hydraulic head. Okay. Wait, where did this? I thought he asked. Oh, he's asking for gamma here. Okay, he's asking for gamma here. I'm going to do what I think it should be. So he took that 998 times 9.81. And that's how he got that. But I would, if he gives you this, that's fine. He does give it to you right over here. But if you're not given, that's kind of the definition of the density of water at that 4 degrees centigrade. So, this must be a different temperature. And then you want hydraulic head at A. Well, then you're just taking the pressure divided by gamma, and you're adding 0. Oh, now here you go. Oh, this is fun. Is this mixing the okay, answers for part A and B are not the same. Okay, that stands as the hydraulic head at C is larger than the hydraulic head at A. Several points are labeled on the same pipe. See figure 2. Oh, okay. Rank these points based on the hydraulic head. Recall that the pipe diameter is constant from the inlet to the expansion. So what do you think? Okay, so point B. I'm assuming that this is the equal thing. Highest and lowest. So the highest and lowest what now? I forgot what it is. Oh, okay. Well, so I'm guessing, do you put it, what happened? Do you move it around? Can you move it around? Wait a minute. Okay, so if I move it off and then move it back on, can I move it to the left? Okay, wait a minute. C. So now what I do, That's funny. Okay. So the hydraulic head is going to be just P plus gamma Z. This is kind of weird. Where's A? So, what the heck? Okay, so you do that. What if I put it in there? It sits next to B. If I put it over here. That's really weird. Okay, so over in F and G, the velocity picked. Oh, no, it dropped. Velocity dropped, so the pressure increased at F and G. So let's see, F and G. Wait a minute. Why does it put that in front? Okay, so do I got to do that?
No, I think it assumes everything in that box is heating equation.
Oh, is that what it's thinking?
Yeah. So there's three different values it's assuming.
That's really bizarre. Because actually, they should make it so you line them up. That's wrong, but I'm just going to submit it and see. It's incorrect. Okay. Well, that'll be fun to watch what people do. Because actually, if you go back and look at the picture, so he wants to know hydraulic head, right? From the highest to lowest hydraulic head. And I've got the picture. And so what happens is, okay, let's see if I can I can erase some stuff. So he is going to claim that right here. Okay, so I'm going to do it like this, and then I'm going to say something happens to where it gets to 0. So right in here, I don't know what's happening between here and here. I'm making that up. So you get to here, your velocity remains the same. It remains the same throughout this pipe until you get to right here. So until you get right here, they're all the same. Then suddenly what happens is, I don't know what this will look like, but anyway, there's a period where it does this, and this is the lower velocity, v squared over 2g. So continuity said this is going slower, therefore this is the lower portion. And so I don't know where he labels this one and this one. This one should be the same as those. This one should be technically the same as this. So if I go back, he wants to know, okay, so I got F. Where's F and G? There's F and G. And then I guess I could put them all over here. Okay, so I guess he would be okay with, he moved them from that to the other. That's really weird. So it's kind of a weird thing. What's the next to do? I don't care about that. Oh, is the next go to the next problem? It does. Okay. Oh, we're out of time anyway. I'll poke around at this one next time. It's a weird question, but it does give you some sense of understanding. So, anyway.
That is why I'm glad you allow multiple attempts.
Yeah. Yeah, this is.
Those are